Hello, today we are gonna see a data structure called heap. This data structure is used in many applications, but the the most important is for implementing priority queues. So the objective of this data structure and what distinguishes the heaps from other dictionary-based data structures is that we want to search for the minimum or the maximum element in constant time. This is the only thing the only objective that this data structure reaches. So we are not looking for a fast search of a given element. Um, we don't focus on searching a general element. Usually the complexity is log n, and we obtain that complexity with other data structures. This is very specific. This is just for searching the minimum or the maximum. It depends if you build a max or a min heap in constant time. So this is the fastest way you can implement a priority queue, essentially. Okay, so having said that, another thing we can say is that this data structure uh, is not designed to look for a given key m, uh, a general key, because the search time is linear, so you can have logarithmic search time with other data structure. This is not the objective of the heap data structure, and you can this data structure is susceptible to change. You can update the heap data structure in log n time. So um, let's say you have a problem where you initially build a priority queue and then you modify the priority queue because the context changes, and you don't want to rebuild from scrap every time the priority queue, because you have a lot of keys, a lot of elements, so it would cost too much. And in that case, you can update the priority queue you initially created, and that is feasible with this data structure. The deleting an element costs log n time. Insertions cost log n time. So you can, after you build a heap data structure, then you can update it without needing to rebuild from scratch every time. Okay, first let's see a practical usage before seeing the insertion, extracting operations that are the operation we are going to see today and the most important. So I prepared for you a practical usage. It is related to a usage related to a video game. This can be implemented to uh, uh, this can be implemented when you have a player. As you can read, you have a player that always shoots to the nearest enemy, and each time a spawn procedure is called, and the player spawns and projectiles with with an interval, a cooldown of 1 second. So you you are this player, you shoot one projectile, then you wait 1 second, and then you shoot another projectile. Okay. Okay. So um, you have a few enemies, and you need to hit the nearest enemy every time. So every time you shoot, you need to hit the nearest enemy. So what can you do? You can build, as you can see in the first image, you can build a priority queue made with distances from the player to each enemy. So D1, D2, D3, D4, you can see the green arrows are the distances from player to enemies. And so you can put in the min-heap in this case, so the smaller elements will be on the left. The smaller element will be on the left. This is the first element. You can build a min-heap adding these elements. And as I said earlier, the the cost for inserting is logarithmic, and extracting, searching for the smaller element is as a constant cost. Okay, so you can build this array up there. This is not a normal array. This is a heap. So this element is the mean element. So after, let's say, so this is a very good way uh, to shoot a projectile toward the nearest enemy, because these algorithms give you the enemy with a very cheap cost. Okay, so let's say that you have a cooldown of 1 second. You shoot an ability each second. So you shoot the first ability, and then after 0.5 seconds, enemies 1 and 2, so this and this enemy, dies. So what happens? When they die, they get deleted. They call a procedure delete from the heap, and this delete procedure will have a logarithmic cost, and then the array will result, the heap array will result in this. So you will have two elements, and now the minimal element is D4. So with this example, I wanted to show you that yes, you can build for a practical context the a min-heap, and you can use it like in the first image. But in the second image, you are not forced to rebuild completely from scratch another min-heap. You can delete elements in logarithmic cost and reduce the heap you already built. So in this case, you have 4 enemies and then 2 enemies, so it seems wasteful to update it. It would be better to rebuild it every second. Yeah, and then it's every second, so who cares? And that's true. But think if you have thousands of tens of thousands of enemies, or maybe you create a projectile every 0.00.01 seconds. So in that case, it's better not to rebuild tens of thousands of enemies. So a cost that is very high every time, but it would be better to update the same data structure. So you can you can either rebuild from scratch or update. But this is a real application. So we built. If you need to launch a projectile to the nearest enemy, you can do it like that. You can build an array like the first here. You can build an array that is a heap, so the first element is the smallest. And then you can simply take the first element, and this costs much less than building than using a list, for example, or an array. Okay, so it depends on how many times you are looking for this minimal element, but this is this is a practical application. Then here I left some considerations about the problem, but I you don't need to see these. If you want, you can pause the video and see what I wrote. So let's go to the second part of the video. The Let's jump back to the heap algorithm. What are the constraints? So constraints of the heap data structure. First, first and most important and most general, this is a data structure of the dictionary type. That means that every node has a key value. We will use nodes. That means we will use nodes containing only the key. So so we are not where usually our node has a data structure in it. We are going to use nodes which contains only an integer and nothing else, but usually this dictionary data structure has for every node they have a data structure which contains something like objects or something like that. For example, you could have uh, a node that contains which contains a person name, surname, and then an id code. And you could use id code as key, and name and surname you would find them through the id. Okay, so these are general dictionary data structure. There are many types. Heaps are one of these kind of data structure. So this is the more general constraint. The second constraint, and this is specific to heaps, there is a mathematical description. You can ignore it if you want. The important thing is you have a tree structure. Okay, you see here you have a tree structure, and this tree structure we consider it begins here where we have 10 and up um, in the upper nodes there can be anything, but we are not interested in that. So there is a tree structure that I will encircle in green that has a root, the 10 node, and a subtree constituted by the pink elements 11, 14, 15, 17. Okay, so there is the 10 and there are the pink subtree. So what an heap says is that for every node, given a node and given a subtree of that node, so node 10 subtree the thing encircled in pink, every element in this subtree is less than the root. So 10 is less than 11, 10 is less than 14, is less than 15, is less than 17. Okay, so maybe here you have some biases because you have studied BST. BST works in a way that the left element is smaller and the right element is larger. So you may see some similarities, but they are not similar because in BST you can have this 10, 11, 14, but you can't have 10, 14, 11. Okay. but 14 and 11 are both less than 10, so it doesn't matter if one is on the right and one is on the left. I am telling this to you because this thing confused me when I studied it. So there is that. Okay, and I think this is the last constraint, yes. We are filling nodes from top to bottom, and then from left to right. So this means that if we want to build a tree inserting 10, 11, 14, and 17, we go top to bottom, then left to right as much as we can, then top to bottom, then left to right, then top to bottom, then left to right. So 10, top, bottom left, the leftiest is this place. So in this place you put 11, then right 14, then bottom left 17, then if you add, don't know, 19 or even 13, you could write 13, okay? This is okay. So top to bottom, left to right, you can't have blank spaces. You can do this, okay? You can do 10, 11, 14, and then ignore all left places because first you have to fill the leftiest places, okay? Okay, and this is the third constraint. Now we are gonna see the two main operations for heaps that are insertion and extraction of the highest priority element, the min element. Before starting with the insertion algorithm for the heap, let's see in what form we will use this data structure. This data structure I presented to you as a tree, the first type. You do remember that I told you that we must go when we build a heap from top to bottom and from left to right. That is because we can, if we do this, we can convert a tree into an array. Simply writing the nodes of the tree structure into an array. So 10 top, bottom left 11, bottom right 13, then we go bottom left 12, 17, 15, and so we converted it into an array. As you can see, the array on the right. So why do we convert this into an array? Because the array as a data structure is better than the arrays are better than nodes and trees, because in arrays you can access the if element in constant time. For example, if we need to do this in the insertion and extract algorithms. But in any case, even if we wouldn't need to do that, an array occupy the same memory, but occupies memory. No, it occupies less memory, and it occupies that memory in static memory, not in dynamic memory. It depends on the array, but if you choose the right arrays, you have contiguous data structure which are memorized contiguously in memory. So it is easier to iterate through an array. You go faster than a tree data structure that is splitted in the memory. in general, if you can use an array form for some data structure is better, and for heaps you can. We will continue to use the tree form because it is more intuitive. You can see better how it works, but in reality we are going to implement things with an array. And with arrays, why do they work? Because you it's easy to find children of a certain father. So the children of the first node of 10 are 11 and 13. So if 10 has an index of 1, then the left child has an index of 2 times 1, and the right child has an index of 2 times 1 plus 1. And this generalizes. So for 13, you can see down here, 13 has index 3. The left child of 13 has index 3 times 2. Okay. So as with 1 times 2. The right child is 3 times 2 plus 1, and the parent is 3 divided by 2 floor. So you discard the remainder. And in this way, we can more easily, we can find father and sons in an array as quickly as we would in a tree. Okay, so searching for father and sons has the same cost, but you occupy less memory, and that memory, if you implement it correctly, it is not in the dynamic memory, but it is in the static memory, and then arrays are contiguously memorized in memory. So an array is not splitted. You don't need to look in different parts of the memory, but it is all there, one element after another.